Hello guys, this is Y, and today I'm going to do another video on multiplication of decimal numbers with logic gates. And in this circuit, the very core of the circuit is the multiplication, where you multiply a binary and another binary number, and you output a binary value. But then if you want to design the circuit so that it lets the user input the value in decimals, then you need a few other components to help you to complete the job. So let's see some of the things we should know, and don't worry, you can find all of their details in my other videos as well as my uploaded files. Okay, so first you input the numbers, and it's going to be in a decimal values. So let's say it's going to have 4 digits. So you are going to have 4 digits of 0 to 9, right? So you need a mod 10 counter so that you can cycle through each of the digits from 0 to 9. So you count to 10 and reset itself to simulate the counting of 0 to 9. So that's what a mod 10 counter means. And then you will have to have a BCD, binary coded decimal to binary value converter. So inside this module, it depends mainly on this chip here. It's not officially called a subtracting chip. I just call that in my circuit. You can call it any other name you want. So it's just a simple module of logic gates that is frequently used in this binary to BCD, BCD to binary module. So that's the most basic module used in this module, used in the main circuit. Alright, so when you have the binary values from 2 inputs, so you have to input 2 numbers. So when you have the binary values from 2 inputs, you need to throw them into the multiplication component, and this multiplication component, it will output your result. So the details on how to build that I will provide, so you don't need to worry about that. And I will explain as well on how do you do it using the logic gate. And then once you have the values ready, you need to perform the binary to binary coded decimal converting. So in this chip, there is a subcircuit used as well, used a lot of times. It's called the adding chip. I call it adding chip because it performs a adding operation. And then another detail on this multiplication component is that it uses a lot of full adder to complete the multiplication process. So a full adder is a component that take in 3 inputs and produce 2 outputs. And the 3 inputs are the first data, the second data, a carry data from a bit before it, a sum, and a carry output. So these 3 are inputs, and then these 2 are outputs. So this is the full adder. And I will explain that in detail later also. And then once you convert it into the binary coded decimals, you can display the binary coded decimals onto the 7-segment displays. So a 7-segment display looks like this. It's a panel with 7 different segments, and you have 7 controls controlling it, right? So you need this component. It takes in 4 input and outputs 7 different signals, and it displays the decimals. So that's overall components on how you do a decimal into a binary, perform the operation, and then binary back into the decimal again. Alright. So the general circuit, it looks something like this. Alright, so this is the circuit, and you can see here there are buttons controlling this circuit, controlling the inputs. So let's say I want to do a 230 by 420 calculation. So I just make it so 230 by 430. So it's just 30. So if you want to correct it to, yes, that's how you correct it. You just cycle through it again. You can see the result here is 96,600. So what this does is, these buttons, when you press it, it outputs the value of 1. When you release it, it becomes 0. So there's one cycle, right? And then these tunnels, these label-y things, they are called tunnels. So this tunnel, it transport the signals to here. So this is a BCD to binary converter, and this is the multiplication component, which is the part where the binary multiplication is happening, and this is the binary to BCD conversion. So because in the multiplication, when you have two 4-digit inputs, you need to consider the maximum output value. So you have two 9,999s, and they are multiplying, they can have a pretty big result. So you need to consider that. So in the process of designing the chips, you need to consider that fact. And so you can see here there are a lot of digits reserved for the output for such cases when it's have to happen. Alright? So this is another BCD to binary, and this is only to show you the numbers you are inputting. So each of these numbers here, they are actually represented by 0 to 9, right? Signals of 0 to 9. But then they are not really binary coded decimal signals yet. They are only just signals sent to this chip. And this chip, it has a built-in counter here. So whatever you tap, it counts only here. So if it counts only here, you cannot just take this chip and get the output, right? So you need to convert it to binary and then use the binary to BCD converter, and then you can take your output here. So these are the two numbers you are multiplying with. Alright, so for you guys to have a deeper comprehension on what we are doing, this is the flowchart of the overall system. So you control the input with buttons, and then you get the counter, and then you go to the BCD to binary, then the multiplication component, which is powered by a lot of full adders. And then you have the binaries to BCD converter, and then BCD to 7 segment, and then only the output result of decimals. So why is it so complicated? It's because that it takes in decimal and output decimals. So if you want the input and output to be binaries, you don't have to worry so much. You only need these two components, these two cores. So these two components are the main characters of our video today, and all the other components, I have videos dedicated to them. And if you intend to have a deeper comprehension about their theories and how they are actually built, you can go watch those videos I have in my channel. Right, so their names are here already. So don't worry, I will explain about their structures in this video as well, but just not the theory of it. Else, if I'm going to explain all the theories and the structures, this video is going to take hours and hours. Alright, so let's start out the first part with a mod 10 counter. So in this video, when we are building this multiplication calculator, we are not going to use the older Logisim, which is called a Logisim 2.7.1. If you search online for Logisim download, the browser will likely lead you to download this older Logisim, but this older Logisim cannot actually handle so much components. So every time I try to open the circuit with the older Logisim software, it actually crashes and fails to load the circuit. So you need to open the circuit with this. Its name is Logisim Evolution. You can search that online, and the version I'm using is 2.13.8. So what's different in the counter component is that in the counter we use a component called the D flip-flop, and this D flip-flop, its full name is data or delay flip-flop. So it stores data. So it can Q output, it can be either 0 or 1 depend on the D and changes upon the clock. So this is what it means. So in the Logisim Evolution, the ports are a little bit different. It's no longer labeled Q0 here, it's just replaced with a negation output, so you can still just comprehend the negation output as Q complement. So in the older one, you have the set here, the preset here. So the preset, whenever the preset is activated, whatever's data in this flip-flop is going to be reset to 0. When the set is activated, whatever data is here, the state of the flip-flop will going to be set to 1. Alright, so this is the preset, this is the set in the newer version of the software. So this is your data and the clock. So you can see their place are replaced. Correct? Okay, so this is their differences of the old and the new software. Alright, so this is the mod 10 counter here. You need 4 of these D flip-flops. If in case you don't know, flip-flops themselves are still consist of logic gates. But as I said, I'm not going to dig deep into the theories. You can watch my video for a deeper understanding, the other video. Alright, so you have this representing 2 power to 0 place. So in a 4-bit binary number, this represents the 2 power 0, this represents the 2 power 1, 2 power 2, and 2 power 3. So what happens, this is the component that controls the reset. So what happens is that upon reaching 1010 in binary, you want it to reset to 0, so that its counting sequence is actually from 0 to 9. So you set up this condition. Once this condition is reached, which is the output of high for these two outputs. So whenever this condition is reached, this AND gate will output a high signal to the preset, also called a reset. So if you call it, if the reset is activated, all the flip-flops will be reset to 0. So this is how you control the counting sequence. Alright, and then you have the binary coded decimal to 7 segment. So when you are building this component, you don't actually need to put this display here also. You don't actually need this. You just need output here, output connecting all the important parts. So you only need output connected. So if you guys don't know what is a subcircuit yet, so due to the massive component count of this multiplication calculator, if you put all of your most basic structures in the main circuit, your computer is going to lag like you've never seen before. Every single operation will take like a few seconds to complete. So it's going to be torturing to work in a condition like that. So you want to maximize the help of subcircuits. So how to add a subcircuit is actually as follows. So you click on the project and you click the add circuit and you name whatever you want your subcircuit to be. Oops. Yes, the naming rule is very strict in the newer program. So if you have this subcircuit, you can see I just put a NOT gate here, and if I just put this and this, so you can see now this subcircuit function as a NOT gate, right? So if I go to my main circuit, you can use a subcircuit within other subcircuits too. So I go to my main circuit, I click on this, I click here, so you can see this is the input, this is the output. So here, now this is a functioning subcircuit. So all of these boxes you see here are actually, all of them are subcircuits. And all of these subcircuits you need to build by your hand. So a very disheartening component is this. It's very painful to build this. It's a lot of components over and over and over again. So you will have to test your skills of copy and paste here. So that's for another day. So let's go ahead and continue on the explanation of this. Alright, so you have 4 inputs and 7 outputs. So this is the circuit for BCD to 7 segments. So you can see that I have labeled the inputs here, so you guys can just have it easy and you don't need to worry about getting anything wrong. And this label here is actually not B, not C, D. So the exclamation mark is actually, you can see the exclamation mark is here, but it's overlapping with the boundary of the gate. Alright. And then let us move on to BCD to binary. So this is what a BCD to binary circuit looks like. And each of these little boxes, they are the subtracting chip I used. So the role of this subtracting chip is that whenever it encounters an input of 8 or bigger, it will subtract 3 to that input. So input 8, output 5, input 9, output 6, input 12, output 9. That's how it works. And you can see the connections here. And don't worry, if you feel that you can make even better optimizations, you can do it with the sum of product expression here. And as to the most basic of the theories on how you achieve these expressions here, you can also refer to the videos I make. And this is how you group them together. So the least significant bit of the least value digit, which is the ones digit, is not tested. As you can see, it doesn't go through any of the chips. And due to this nature, and each of these chips having 4 inputs, the last chip at the end will have one of its input empty. So you just connect a 0 input here, and you don't need to change this input. Alright, this is how it looks like. Then it's just connecting the chips here, connecting the chips here, and each layer you shift, one bit just move all the way down to be the output value. Alright, so all the way until you connected to the end of the sequence, and this is actually the 0 input here. So why end here is because that if you have one other chip down here, these two pins, there are only 2 meaningful pins, as this pin, it will always output 0, because for all the inputs, for all the possible inputs you are going to have, this output here will always be 0 due to the fact that the bigger numbers are minus by 3, and you will not have a 1111 number when you are actually comparing it in the ones place. So what do I mean it by ones place? You can refer to the video. This is actually the shift and entry, the reversed shift and entry algorithm. So Yeah, you just have to know how this is built right here. So if you only have two meaningful inputs, the biggest value is going to be is 1, 1, and that's 3 in decimal. So 3, we don't need to modify it anymore, so you don't need any more testing chips down here. So this is the BCD to binaries. So this rightmost line here is going to represent 2 to the power of 0. And then the second line here is going to represent 2 to the power of 1, and all the way, just following this sequence, this increasing sequence. A very similar thing is that you have binary to BCD, which is just the reverse of the circuit just now. And you can see the connection is already drawn here, and the sum of product expression is given here as well. And the way to build this circuit is very interesting. It's just the inverse of the other circuit, the BCD to binary circuit shown just now. So this is a 16-bit input binary to BCD, and this one here, it is the 16th bit. This here, the 16th bit. So why are there 4 extra bits here? Is because due to the nature of the requirement of this circuit, each time you add a layer, you will have 1 empty input. So this is the nature of this circuit, the nature of its design, and the reason is hidden in the most fundamental of the basic operations of this algorithm. So if you're interested, you can check the video out. And they are connected, and the same thing, what happens is that the least significant bit here, it is not tested, so all the way down here is just here. So what a binary to BCD conversion do is that this 4 place, oops, my pen is not right. These 4 outputs is going to represent the ones. These 4 outputs is going to represent the tens. These 4 outputs is going to represent the hundreds. So it's arranged in this way because a binary coded decimal is only from this here to this here. So you only need 4 outputs, right? That's the nature of the codes. Okay, so we have this down, and let us move on to how the full adder will look like and how they operate. So let us start off with what's a full adder first. The most basic unit that forms a full adder is called a half adder. A half adder, it adds 1 bit of information. So you can see here, you have 2 zeros, you get a result of 0. You have a 0 and 1, if you add them, you get a result of 1. But you have 2 ones, you get a result of 0 with a carry of 1. So whatever's in this column here, it is called a carry, and this is called a sum. So you see you have the sum and the carry here. So if both, let's say this is A and this is B, if both of them are 0, sum and carry are both zeros. If either of them are 1, you have a sum of 1 and carry of 0. If both are 1s, you have a sum of 0 and carry of 1. So instantly you can observe this pattern to it is exactly the similar pattern to how a exclusive OR gate works, and this is the exact pattern of how a AND gate works. So instantly you can see that this is AB and exclusive OR, and this is sum, as well as this is AB input and this is the carry output. So if you combine them, the half adder looks like this. AB, the exclusive OR gate, connected to the sum, and the AND gate connected to the carry. And you can see in the exclusive OR gate, it only output 1 when the input are different. So it only have 1 when the inputs are of different states. And then carry is only 1 when both inputs are 1, and that is exactly the working principle of an AND gate. So this is a half adder here. So what's a full adder? A full adder is basically two half adders concatenated so that it can take in 3 values instead of 2. So the other value that a full adder takes in is the carry input. What do I mean by the carry input is that in a half adder you have 2 input and 2 outputs, but in a full adder you have 3 inputs and 2 outputs. So the extra input, it is actually a carry in, and what this carry in means is that it is a carry in from the last bit. So for example, if you have something like this, if you have something like this, you know that this here is A, this here is B, right? So you know that this, and then you don't have any carry values here, so the carry at this bit is 0. But then if you sum this, it will carry 1 to this place, and the sum here will be 0. And now you have a carry of 1 at this bit. So a carry of 1 means that this carry input is 1 now. And A is 0, B is 1. So 1 plus 1, it carries to 1 again. And this here is 0. So again, this here have a carry of 1. But now A and B are both 1s. So you have 3 input of 1s. So now you have another carry of 1 to the other place, but now the sum here is 1. And then you have 0 and 0 for A and B here. Just the carry of 1, so this is 1. So 0, 1, 0, 1 plus 0, 1, 1, 1 equals to this number, right? So how do you design this? First, you must form the truth table. So when there are all zeros, you do not have any sum or carry. So when either of them are 1, you need a sum of 1 and 0 carry. Either of them 1, you have this combination. So this here has only 1 as well, so you have another combination of this. But if both 1s, you have a combination of 0 sum and a carry, right? So if you have 2 1s, you have a 0 sum and a carry. 2 1s, you have a 0 sum and a carry. And then 3 1s, you have 1 sum and 1 carry. So this is your Carnot map, truth table. And you can use this to form a Carnot map, like this, right? You just mark the 1s at the place designated, shown here, and you can find the sum of product expression here. So I'm not going to go through step by step how to find that. It is very basic knowledge in digital logics. And you can see how do you transform this expression into an expression expressible by logic gates. So you have this expression here. I just write the same thing here. And we know that in exclusive OR gate, the formation looks like this, right? A x0 y and a x y0. So this expression, we can factor out the c value, the c here, the c here. So you take the ab and the ab here, right? And then you factorize out the c0 here. So you have the c0 and there are combinations here. So it's just algorithm. So now the point is that you must realize you have a, let's say that you have c as x and this one as y0, and then you have an x0 here, and then you have a y here. So this is the exact pattern of an XOR gate, only that the y is represented by 2 variables. Now I'm going to explain how to recognize this. So how do you recognize this is that you can see that exclusive OR, it applies this formation, right? You can see the same formation in this bracket. Also, if this is y and this is y complement, that means this expression here must be a complement of this expression, which is the complement of an exclusive OR logic. So if you do in complement of exclusive OR logic, you apply the De Morgan's law. I hope you know what is the De Morgan's law, because if you don't know De Morgan's law, you wouldn't have encountered this video as well. So you just apply the De Morgan's law again, and you expand this expression. And this is another law where if A is multiplied by its complement, it is equal to 0. So this one here is equal to 0. This one here is equal to 0. So what you have is, which is the complement of exclusive OR. So now you have proven that this term here is in fact the complement of this term. So it goes along with the general formation of this, and now you can actually see that. So A and B, they are going through a exclusive OR gate to get both of these formations. I mean this one here. And then you let this output to go through another exclusive OR gate with the C input, so you get this overall expression. So this is what its structure looks like. Alright, so now for the full adder, you have the building of the sum. So what you want to do now is the building of the carry. So for the carry, for this exact same thing, you just mark them down, so you get this expression, right? Now this expression, you need 3 AND gates and it's not very efficient. So another useful step when we are doing Boolean algebra is that we can write something like this. So we can see this is an expression with 3 variables. So when the variables only use part of them, you can see that BC does not have the term of A. So you can actually express that is ABC plus A naught BC, right? This is equal to BC. This is one of the laws. And if you're wondering how this comes from, I can just BC multiplied by bracket A plus A naught, which is BC multiplied by 1, which is BC. So this is how it came from. So you need to learn from this to this. You need to learn to take this to this. So this is one of the steps. Can be easily ignored, but it's a good technique in solving Boolean algebra. So now you can do, let's just leave AB alone, because we can see that both of these terms share the variable of C. So so let us get this ABC and A naught BC from here, and then ABC plus A B naught C from here, the missing B variable. And then you know that in a expression, A plus A equals to A, right? So the same thing is that ABC plus ABC. So you only have one of them. So you can just cancel the other. And then as well as this here, you can factorize them. You can take the piece AB now, and you can see this is C plus 1, right? This is basically A times B times 1. So you can see you can factorize C plus 1 here. And then you have this. Alright. So now you have something like this. And what is this? You can factorize this into A. You can factorize the C out. And you will see that similar pattern again, the XOR logic. So what this is that it is in fact a B gone through a AND gate and a C, and we have AB gone through a exclusive OR gate, which we can take from this sum here. This is the part we want. This is the part we want to take from here. So you can just take it here and you put it together with C. So this is another AND gate. This is A exclusive OR B. So now you add them together and you have the building for the carry. So this here is the carry. So this is how you form the sum and carry of this full adder. So now you want to assemble them into the complete full adder. It's just something like this. AB goes into here, C in, carry in, and then you have, let's just add the AB here first. Add the AB, C in, and you want a AND gate here, which takes this output here, and then you want an OR gate here, and this forms the carry out. Alright, and this together with expression this here, the C here, goes through another exclusive OR gate and it becomes the sum, right? Alright, so now we are finally getting to this multiplication. So this is the main character of the main character in this circuit. So let's try to do it by hand first. So what the multiplication is going to look like is that when this is 1 here, you just write the sequence of this upper number. So when this is 0, you don't write anything and just all zeros, right? Because it's multiplying by 0. So this is 1, you just write, you just repeat the number here. So if it's 0 and 0 and 1 and 1. Alright, so this is how do you do multiplication by hand, right? So it's actually more easier to explain than the BCD to binary and binary to BCD conversions. So what you are going to realize is that multiplication, ultimately, it is still made up of additions as well. That's why you have addition here. So you have addition here, right? So for this here, it doesn't go through any addition. So just straight down, it becomes the result. So this is one clue is that the component at the top right does not need to go through any conditions. Alright, so this here, it needs to go through one adding operation. So you need to add them, right? So if in case they are both ones, so you need to have a carry, right? So if they are both ones, it will result in 1 0, and this one will be a carry value. So if you are carrying it, it will affect this addition, right? Okay, so now you know that they will affect each other by carry, and then we can see that the number of addition is increasing. You have 3 additions here, you have 4 additions here, right? And then you have 3 additions here, 2 additions here, 1 addition here, and you don't need any addition here. Alright. Be careful on this. Even if you don't need to perform any addition here, the case is very different from the first case. Because what? Because it is still possible that a carry is going to happen. So in this case, a carry is brought here. So you have a carry of 1. So 1 plus 1, you need to carry as well. So this is where you want to look up for the logic. Alright, so since it's going to be in a using full adders as the most basic component, so our full adder is going to be designed in this way. So you have 3 input and 2 outputs in a full adder, right? So I put the first data here, the second data here. This is the carry in because the carry in is taken from the bit to the right? So I design it to be here on the right, and the carry out to be on the left. And then the sum is located at the bottom. So you can see the sum of these two is moved onto here. So this number will be dealing with the sum of these two. Alright. So for the first component, you need to realize that this row of values, they are actually made from the multiplication of the values from these rows, right? Let's say this is number A and this is number B, and the smallest digit is indexed 0. So this one here is actually A0 B0, right? So it's actually a AND gate, right? AND gate of A0 and B0, and this is your output. So what's going to happen is that you have I should write it more to the left. A0, and here you have the B0, right? So it's going to be AND gate, AND gate, AND gate, AND gate, AND gate, and you connect each of the A's, and then the B are connected to each of these AND gates. So this is your output, and this represents the first row. And since this first thing is not going through any of the full adders, so you don't need to do any full adders for it, so it's just straight to result. And then for this here, you need to add it with a number. So this number is represented by, so where is this number going to be? This number is the first place of, is the 0th place of the A number and the first place of B number. So in fact, it is actually A0B1 for this. It is in fact A0B1, right? So what are you going to do is, when you are doing this operation, you are going to need a full adder, and the full adder is going to take the sum as well as the full adder is going to take the sum, right? So this is the AND gate, and you are going to take the sum here. The sum is going to play one part, but then you need a value of A0, so you need to drag A0 all the way down here, and then you have B1 here, so that it represents, this one here represents A0 B1, which is this thing, and then the sum represents this thing. See, this is the second place, which is this place. So you actually have something like this, and to here the same thing happens, which this is now from A1, and then this input here is B1 as well, but then you need the carry, right? And the carry is from where? For this row, the carry is from the left row, is the left column, right? So the carry is actually from here, supposed to be from here. So if you have another layer down here, right, you are going to have the carry out connected to the carry in. So that's how it's going to look for the lower levels, and the sum is going to be here, the AND gate is going to connect to your A inputs, so the A inputs is propagated all the way down here. So you have B2 here, you just connect to the AND gate as well, and B2 is connected to this AND gate as well, and then you have A1, the value of A1 here, and then you have the sum connected, the sum of the vertical above flip-flop, you connect the sum here to the data 2 port. So this is how it's going to look like. It's a sequence you can see is all the same thing over and over again, all until the last row. So everything you have here all until the last row. So what the last row is going to be is that you can see that the last row it is only the B and the A. So you don't need to consider adding them. You don't need to consider the sum. So I mean, due to this fact, due to the probable having one more bit here, you actually need to consider this one. So your last row is going to be this. So this is your second last row, and all the way to your second last row, you are still going to use this design here. So for your last row, this is the last row, which is the results. Your last row is only going to consist of full adders, in which you are trying to see if there are any carries like this one. So the last row is going to be just full adders. The values is just going to be full adders, and it takes in the sum here. Let's say this is vertically just below this full adder, and they are actually side by side, both of them. So you actually need this, and then you have the carry, and the carry will actually go to another input, go to the input of another column of the full adder. So this is what it means, right? Your carry goes to the other column. So your carry always just goes to the other column. So this is what it means. So the sum moves down, to your results, and the carry goes to the next column, and see if the next column will have a similar sum, and then it will need to propagate again to the next column. So this is what happens. And then for the fact that you can have, let's say you have three ones together. Let's say if you have four ones, what is going to happen is that you will have this as a result. So it actually moves two columns across, right? So you have two columns across. You need to consider, because if this add this, it will produce a carry. This add this, it will produce another carry, and this add this as well produce another carry. So you have a sum, a carry, and a carry. So what is going to happen is that this here, and even if you are at the last row, you are going to still result in a carry as well. So you are going to connect the carry like this. So in this here, the first column is not going to have any carries, as well as this here, because you can see that there are empty spaces here. So whatever carries is already propagated. So only at the start of the second last row here, you need to consider them, this bottom level full adders. So the first digit of the bottom level full adder, you need to have a 0 carry in. So you need to give it a logic level 0 here, and it's going to connect like this all the way to the last. So what's going to happen here is that a maximum output of binary digits with the multiplication of two 5-bit binaries, it's going to result in 1, 2, 3, 4, 5, 6, 7, 8, 9, and possibly 10 columns. So you need full adder, the last row full adder starting here, 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 and here. And these are results from the upper level full adders. So this is how the general structure is going to be like, and you can observe more of the details in the smaller version, the scaled down version of the circuit I designed. Here you can see this. You can see this is a 1, 2, 3, 4, 5, 6, 7, 8 by 2 bits. And you can see if you multiply If you multiply 12 by 2, it's going to be 24. So 1, 2, 4, 8, 16. So 8 plus 16 is 24. So this is how it's going to work. And you can see that the most upper level is only AND gates, and the most bottom level is only full adders. And the middle levels, they are consist of both AND gates and full adders. And then you can see this is a 0 input, which you need to always keep it 0. And you can see the 0 input is connected to every single row for every single middle row added. At the leftmost full adder, you need to add this 0 input, and as well as the first full adder at the most bottom row. So you can see the 0 input is dragged all the way here, and this is your 2 power 0 output, 2 power 1 output, 2 power 2 output, all the way here. So if the first number you have 8 bits, for every single row you are going to have 8 such group of components, 8 units of them. So you can see in this middle row you have 8 units of the combination of full adder and AND gates. So this is how you do the connection. And if you want to do it on a full scale of the full scale capable to load a 4-digit multiplication, is going to require you to have all the way up to 2 power 14. So there's a total of 15 by 15. So 15 on the one input here, and 15 on the second input here. So from 0 to 14, so a total of 15. So you have a circuit like this. So I forgot to remove the unnecessary full adders here. So even if you just remove the full adders here, it's still going to work fine. So I just forgot to remove it from the last time I designed this circuit. And this very weird naming of these inputs are actually because I did this design on the older Logisim software, and when I migrate it to this new Logisim software, due to the illegal naming system, so the system just changed to random digits like this for me, and I'm lazy to change all of them back. So yeah, that's why they look funny here. And you can see some little details are that the logic level zeros are here. The A14 signal is propagated with every single layer, as well as the A13 signal. You can see here is propagated down. It's propagated down, right? So this is how the structure looks like. If you want to do it in a full scale, and don't worry, I will upload a file consists of pictures of these circuits in a PDF, and hopefully through a Google Drive link, and you guys can watch and design step by step. Alright, so this is how the multiplication works, and basically that's all the components in this circuit. And now let us go and observe again. So this is our main circuit here. It's I call it multiplication. And then here we have the buttons, tunnels, all the components are in place. You can switch it to the simulation mode. You can see the components moving. And one thing you can see is that it actually lags a little when I press the digits here. So what this means is that the system actually goes through so much recursions because there are subcircuits, and there are also subcircuits within the subcircuits, and then you have all these subcircuits connected together. It's going to be a lot of recursion of signals, so signals passing back and forth between those subcircuits. So what happens is that this will eat up a lot of system performance. So if you try to open this circuit in the older Logisim software, as you can see, this is the Logisim evolution. If you try to open it in the original Logisim software, it is not even going to render correctly. Moreover, try to read your signal. So this is the reason why I changed to this newer software here. Not only the code is more efficient, apparently it can have more components too. And yeah, I hope you guys have a good understanding on this video and the way I explain how those components work. And thank you very much. And if you have any suggestions or questions or critics, you can leave it in the comments. I will try to help as best as I can. And thank you very much.